Okay, this is lesson 4.4, multiplication rule. Now, with multiplication rule, we're looking for the probability of A and B, okay? So the probability of two events occurring, probability of A and B. Now, to point something out, we're going to talk about this a little bit more here in a little bit, but this means the probability of B after knowing the probability of A, okay? So A has already occurred. So A has already occurred, we want to find the probability of B, knowing that A has occurred. That's what that means. Now the formula for multiplication rule is this. If you're looking for the probability of A and B, then you're going to find the probability of A and multiply it by the probability of B. Okay? Now this brings in some situations for us with multiplication rule. The first one is what we call an independent event. This is one event, or it's looking at two events where one event does not affect the second event. An example of this that I often use is marbles. Let's say you put in a bag red, green, blue, and purple marbles. And you randomly draw one marble, and then you put it back in there, and then you draw another one randomly. The first event does not affect the chances of the second event because you replaced the marble. So usually independent events deal with replacement, or the two events don't affect each other at all, okay? So if I want to know the probability of drawing a red marble out of my little bag, and I draw a red marble, but I put it back in there, I have the same probability on the next drawing of getting a red marble as I did in the first drawing, okay? Independent events. The first event does not affect the second event. Dependent events, however, this is when the first event does affect the results of the second event. An example of that is, let's go back to the marbles in the bag. If I wanted to find the probability of drawing a red marble, well, I would draw the first marble and not replace it in the bag. And then I want to find the probability of drawing a blue one. Well, the probability of the blue one is affected by the red one because now I have one less marble in the bag. Or if I draw that red marble and I want to know the probability of drawing another red marble, it's doubly affected because now I have one less marble overall and one less red marble to choose from. And so that probability is affected. So that is dependent events, when the first event does affect the second event. Not effect, but affect. All right, an example. Of the 50 people who use drugs, going back to our drug thing up there. Of the 50 people using drugs, find the probability with replacement of drawing two randomly where the first is a positive result and the second is a negative result. Okay, so we're going to find the probability of A and B. The probability of the first result, okay, was we're going to with replacement, okay? So this is an independent event. So there are 50 people, right? And we're going to do two drawings here. So the first one is, we're looking for the probability, the first one has a positive result. So probability of a positive, and the probability that the second one is negative. So to solve this, we want to find the probability of A times the probability of B. This being my A and this being my B, right? So let's look at the probability of an A, of positives, okay? So of the 50 people using drugs, these are the 50 people using drugs, there were 44 that were positive. So 44 is what I'm looking for, out of the total possible, which is 50. That's the probability of A, times the probability of B. The probability of B is a negative result. There are only 6 negative results, and so we would have 6 out of 50 for event B. Now you guys, you can just plug this into your calculator. You're looking for a decimal answer. the decimal answer you will get is 0.106. Okay, so that's the probability of those two events occurring using multiplication rule. Now guys, we're going to do this again, the exact same thing, only without replacement. So that means we're going to look for a positive result and then not replace that result and look for our negative result. So the first event, looking for a positive result, is still going to be 44 out of 50. However, because we don't replace that result into the probability of things occurring, it doesn't affect the negative because we are looking for positive, so there are still 6 negatives. However, there are no longer 50 options for the second one because one of those options was taken out, so there are only 49 now possible to choose the negative from. Now you multiply across the top and across the bottom, you just plug it in your calculator. The probability of this occurring without replacement is 0.108. Only slightly higher than the other one. They're both 10% basically. 10.6, 10.8%. But that is the difference of replacement with non-replacement. Alright, here's another example. At the airport, there are 102 scales that were found to be defective out of 810. So if we were to randomly select 2 different scales with replacement, we want to find the probability that both of them are defective. Okay? So we have 2 events. These events are going to be both defective. So event A is defective and event B is also defective, okay? Alright, so once again, this is with replacement on the first one. There were 102 defective. So the probability of my first event is 102, and that was out of 810. We're going to multiply that by the probability of the next one being defective. Because that's thrown back into the mix because it was replaced, it's the exact same probability. There are 102 possibilities of defective and 810 scales. We multiply this out and the answer we get is 0.0159. Okay. Without replacement, okay? This is what's going to happen without replacement. The first probability of defective is still 102 out of 810 because there's nothing affecting that result. We're still looking for a defective one. That's 102 out of 810. However, that one is not replaced, which means 2 things are being affected here. There are now only 101 defective scales because one of them was not replaced, and there are only 809 scales because one of them was not replaced. One of the defectives was not replaced. That's why there's 101 defectives. Now if this was defectives and this was working, then these numbers would all be different. But the reality is, because this one was defective and it wasn't replaced, there's only 101 defective machines left. When you solve that, you get 0.0157. Now guys, these aren't showing significant differences, but there can be significant differences. It's just the idea of helping you identify the whole replacement with independent events and the non-replacement with dependent events, okay? Now, let's just go a little bit further with this one. Let's say there's 10,000 scales and 1,259 of them are defective. We want to find the probability without replacement of 5 randomly chosen scales that are defective. Okay, so these numbers are all changing, okay? We have 5 defectives. This would be defective and defective and defective and defective and defective, okay? So that's how this is going to work. The multiplication rule still is the same though. If we are looking at them all being defective, what's going to happen is this. The first one, there were or sorry, 1,259 defective out of 10,000. Now, because these are without replacement, and we're doing 5 of these, we're now going to subtract 1 from each of these and continue down. 12, 5, 8, 9, 9, 9, 9. And then 12, 5, 7, and 9, 9, 9, 8. 12, 5, 6, 9, 9, 9, 7. 12, 5, 5, and 9, 9, 9, 6. You could solve all that out, and when you do, what you get is 0.0000314. Okay, now guys, that's technically how we do it. Now there's a rule called the 5% guideline. And what that states is this: if the sample size, which in this case was 5, that we were choosing from, is less than 5% of the population in this case being 10,000, so if it's less than 5% of the total amount in the population, we can treat it as an independent event, meaning we don't have to reduce it by 1 each time. We would have 1259 over 10,000. The next one would be 1259 over 10,000. The next one would be 1259 over 10,000. We can treat it the same as an independent event because the probability is so small. That it's such a small, 5 of them is so small compared to 10,000 total population. Now the reason why this is nice, I'm going to put 3 dots to indicate that we're going on through 5. The reason why this is nice is because this is what this does for us. What we would end up doing here is 12,059 over, not 12,000, I keep saying that, I don't know why, 1,259 over 10,000, and we can raise that, since we'd be multiplying that 5 times, we can raise it to the 5th power, which is the same thing, and the answer we would get is, let me find my answer, 0.0000316. Not a whole lot of difference in those 2 probabilities. And so because it was less than 5% of the population that we were drawing in our sample, we could use independent events to help us solve it, to make it easier. Now guys, we have to consider carefully the events being considered, okay? For example, 2 people in this class are chosen to have equally likely birthdays during the week. In other words, everyone has the same chance of having one of 7 days, right, for their birthday. So, we want to find the probability that 2 people chosen in this class are born on the same day of the week. Well, the first person, guys, can be born any day of the 7 days. Basically, 7 out of 7, right? They have that option because there's nothing restricting them. But the second person has a restriction. If you think about it, they have to be the same day as the first person. So they have a 1 in 7 probability. Well, because the first one has a 1 and the second one has a 1 in 7, the first one has all 7 days, which basically means they have a probability of 1. If you were to multiply 1 times 1/7, because the first person has all 7 days, that would be 7 out of 7. Let me just write that. 7 out of 7, which is 1. 1 times 1/7 would be 1/7. Your probability would be 1 in 7 still, okay? Because of the wording and because of how the first one does not really affect what's going on with the second person. Now, if we were looking at the probability of 2 people being born on Monday, that's different because now we have a specific day that the first person has to be born on. The first person has to be born on a Monday. So that means that person has a 1 in 7 chance of being born on a Monday, and the next person also has a 1 in 7 chance of being born on a Monday. We multiply this out, we get a 1 in 49 chance of them being born on a Monday. These are independent events because the first person's birthday does not affect the second person's birthday, so they're independent. We don't have to subtract one or anything, and that gives us that answer. Now, hypothesis testing, guys. Let's look at how we can identify whether or not a hypothesis is correct or has value. Okay. First off, we talked about gender selection in the past, and it's designed to increase the likelihood of having a girl. Let's just say that. Okay. Let's say it's designed to increase the likelihood of having a girl. So assume 20 couples have 20 babies, and all of them are girls. Now, assuming gender selection has no effect, okay? So when we're testing a hypothesis, we're first going to test it as if it has no effect on the result, okay? No effect. That means that we would have a 0.5 probability for all 20 kids. So first kid would be 0.5 times 0.5 for the second kid times 0.5 for the third kid on down to the 20th kid, which would be 0.5. We could solve that by just doing 0.5 to the 20th power, and that would give us 0.0000. See how many zeros I'm going to have here. 1, 2, 3, 4, 5, 6. 954. This is such a small number. There's really a 0 probability of this occurring, right? There is a 0 probability of you getting all girls, basically. Okay, it could happen. But it's basically a 0 probability of getting all girls. Now, let's give you some actual results. Let's say that there were 945 babies and 879 were girls. Okay, so let's just take our hypothesis and assume that the probability of this occurring is 0, okay? Now we could solve this, guys, and we'd find out that the probability of this is not 0, but anyway, let's just say the probability of this occurring is 0. If the probability of this occurring is 0, then, sorry, I gotta get my brain wrapped around what I'm saying to you here. If the probability of this is 0, then that means that this result couldn't really happen, right? Unless this gender selection thing was actually effective. The only way you're going to get, assuming that you should have a 50-50 chance of boy or girl, and 879 is not 50% of it, or even close to 50%. So there's a 0 chance of this happening, of you getting 879 girls out of 945. Then what that does is actually proves that the gender selection works because there's 0 probability of this happening. Okay, with our first hypothesis there was 0 probability, and so with there being 879 girls out of 945 having a 0 probability, we can now assume that the hypothesis that the gender selection works is actually true hypothesis, and it works. Hopefully that makes a little bit of sense. We found out that there's a 0 probability of this occurring, and then applying that to actual results, there being 0 probability of 879 girls being born out of 945, we can assume the hypothesis of gender selection working being true, okay? Now redundancy is duplication, okay? So an example that they're using in the book is they're talking about aircraft. Aircraft have duplicate components, like 3 hydraulic systems, okay? And there are other duplicates besides that, but this helps with the probability of the plane failing. If one goes out, then the next one kicks in, and if that one goes out, then the next one kicks in. making it extremely unlikely that your hydraulic system is going to not work for your flight. Okay? Now, let's say that the probability of failure is 0.002 in this case. So we're going to have a 0.002 probability of failure. That is my actual probability, okay? So we want to find the probability if we only have one hydraulic system that it does not fail. So this is the probability of failure for one of these. We want to use a complementary to find out the probability of success. So for only one system, it would be 1 minus 0.002, which gives us a 0.998 success, okay? That's just for one hydraulic system working and not failing. You have a 0.998 probability of success. Okay, that's good news. I mean, you have a 99% chance that you're going to make it to your next location without a wreck. Now let's include all three of these hydraulic systems in this, okay? So with all three of them, find the probability that it does not fail. So let's first find the probability of it failing, okay, for all three. Now guys, these are three different events because there are three things going on here. So the probability of this failing would be 0.002 times 0.002 times 0.002, because that is the probability of each one of those failing. That gives us 0.00, there's 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and then 8. That's the probability of failure, okay? That's really good news, to be honest with you. But we want to find the probability that it does not fail. In other words, the probability of success. So again, we're going to go to the complement of that. 1 minus this answer, I'm just going to put ANS for answer, so I don't have to rewrite that, is going to give me 0.9999999, 1, 2, 3, 4, 5, 6, 7, 8, and then a 2. That is pretty high probability. It's basically 100% probability that your hydraulic system with three of them will not fail you on a flight.